last time. So let's take a look at this one. Let me remind you while you're reading this, notice it says, you read through that a little bit, it says, on the closed interval from 0 to 12, what is the maximum distance between g of x and f of x? So when we are talking about maximums or minimums, where do we get our candidates for these maximums and minimums? Maximum and minimums occur at critical points or endpoints. So two different things, but they make up the candidates, right? So critical points or endpoints would be our candidates. I'll read this one out loud for you while you're reading. It says g of x is x to the 1/3. F of x is 1/4 x. On that closed interval from 0 to 12, what is the maximum distance between g of x and f of x? Show the work leading to your answer. So whether this is calculator active or not, which I think we will make it calculator active, this is complicated enough where just like going max min might not be the easiest thing, and you can't even do that anyways. So let's work on this. Candidates. What are the easiest candidates? 0 and 12. They're right there. Endpoints. So we can list those out if we want. I'm going to say that right here. My candidates are x equals 0, 12, and then possibly some critical points to go along with those, right? So, kind of a different question, right? I mean, it says maximum distance. So, I don't know, it feels a little bit like a wordy problem, kind of like the related rates. It's definitely not a related rates question because it's not asking us to relate any rates. It wants to know the maximum distance between two functions. So let me ask you this. How is it that you would find the distance between two functions? Okay, now, yes and no. It is derived from the distance formula. But if I were to write these out, maybe don't copy this down perhaps. If I were to graph these, the graph would look like this. X to the 1/3 is about like that. And x to the 1/4 x, of course, is just a line. So, I don't know, maybe it would look something like this. I honestly don't know which one is higher on the interval. I do know they both go through the origin, right? But beyond that, I'm not sure which one's higher. So I don't know if it's like that or if it's like that. Let's pretend like it's the first one. We could use the calculator here in just a moment to figure this out. How would you illustrate the distance between those two graphs? A vertical, all lines are straight, a vertical one, yeah. So a vertical line, maybe something like this, or something like that. And so if I'm going to think of the distance as a vertical line, how would I express the distance between the functions? And you could express that by subtracting, right? Subtract high minus low. So let's take a second here. Let's use your calculators and graph these and decide if one of these graphs really is consistently higher than the other one, because they might even cross. I mean, who knows? We didn't even talk about that possibility. It could be that the graphs do something like that. We could have parts where the red is above the blue and other parts where the blue is above the red. In fact, I think that might be what this is, if I remember correctly. Anybody have a take on that? Do they cross? They cross, yeah. Okay, so for the first part, I'm guessing the 1/3 is higher. And then after a while, the line is higher. So it looks something like that. Okay. So Jake, I think if you increase your window to go 0 to 12 on the x, I think you'll see the cross happen there. Yeah, so this is a little bit different, right? As far as like, all right, which one's the high and which one's the low. The good news is we're talking about distance. And so distance is always a positive number. So it honestly really does not matter which one's high or low. We can kind of hash that out in the end. But Jake's idea of we need to take g of x minus f of x, or maybe f of x minus g of x, that's going to be the right idea. That's how you find the distance, the vertical distance between any two functions. This does come from the distance formula. Do you want me to show you how real quick? Check this out. So if we said, we've got maybe right here the distance from this point here to this point right there, that would be a vertical pattern, wouldn't it? So in a vertical pattern, wouldn't it be fair to say that the x coordinates are the same? So you could say distance squared. Well, let's not even do that. Let's just go distance equals square root of the difference in the x coordinates squared plus the difference in the y coordinates squared. Well, wouldn't delta x be 0? Yeah. Because it is a vertical pattern. So it'd be d equals square root of 0 plus delta y, that's supposed to be a delta there, squared. Well, what's the square root of delta y squared? Delta y, the squared and the square roots cancel each other out, and delta y is simply one function minus the other function. So we could in the end say the distance between them is like y2 minus y1, f of x minus g of x minus f of x. Does that make sense? I want to be able to connect those for sure. Okay, you guys are really, really quiet right now. Is it because of the weird transition from courtroom drama to math? Are you following with me? This is an honest question. You need to be able to make this transition. Are you doing okay? Jackson's just, I don't know. You kind of stared at me, so I'm staring back.
Oh, I just looked over because you asked me a question.
Do you guys, are you doing okay? You're being awfully quiet. Ask a question if you're confused on anything. Okay, so we're going to say, based on our picture and our reasoning there, we're going to say distance equals, Jake, since you suggested it to begin with, which one do you want to be minus which one?
I would do d of x minus f.
So x to the 1/3 minus 1/4 x. All right, fair enough. So that's our distance. So we have our candidates at the endpoints 0 and 12. How do I find my critical points to go along with those to fill out the candidates? Critical points are places where? And so we're dealing with d's and x's here, so I'd maybe say like d prime. So Josiah is right. We need to find d prime. So we're going to write d prime equals, and let's figure out what d prime is. Alex, what would d prime be for this particular question?
D prime would be, let's see, 1/3 x to the negative 2/3 minus 1/4.
That's exactly right. Nicely done. So now we want to find out where d prime either doesn't exist or is 0. Is there any way that d prime won't exist? Careful. Is there a denominator in there? There is, right? Because the x has an exponent of negative 2/3. So doesn't that mean that that x is really a denominator?
Yeah.
So what number would make d prime not exist?
0.
We already have that in our candidate list though, right? So even if you mess that one up, it would not have been that big of a deal because it's already in the candidate list. So you make note of it, but it's not going to make any difference here. It did before, but not here. We want to set this equal to 0 now to figure out where is d prime equal to 0. A little bit of algebra here. Any suggestions on what you would do first? All right, yep. So 1/3 x to the negative 2/3 equals 1/4. That's a good move. Okay, so x to the negative 2/3 then would equal 3/4. Calculator is active here, so what might you do to finish this one off?
Just do 3/4 and negative 2/3.
No. Close. Yeah. I want to take both sides to the negative 3/2. This would work.
Oh, yeah.
You want to take it to the reciprocal power, right? So wouldn't the x to the negative 2/3 to the negative 3/2 just end up being x to the first?
Yeah.
Right? Because you multiply those exponents. And then we use our calculators to figure out what is 3/4 to the negative 3/2. And that will be our lone critical point. So once you've got that number, please inform us what you got.
1.5.
Sorry, say again, Zach?
1.54.
Let's at least go 3 decimals.
It's 0 because it's 1.5396.
Give me one more. 1.54.
1.53.
Oh, 5396.
Yeah. If you write it to 3.
Got it. Yep. So just a note here, of course, really important that we don't use rounded values later on. It's fine if we want to round off just to make a note of what we're talking about, but let's not use those later on. Okay, so the final thing we need to do is take our candidates and decide which one is going to generate that maximum. We've got 3 of them. I've got 0, 1.5396, ... and I've got 12, and I want to figure out which of those generates the biggest distance. So what am I going to plug those numbers into? The original, the D, right? I'm going to plug them back into this one right here. So again, definitely calculator active. It'll be helpful on 2 of them. When x is 0, what's D? 0. You can see that on the graph, and you can see it in the numbers fairly quickly also. But when x is those other 2 numbers, it's going to be less obvious. So let's run the numbers in the calculator. Anybody have one for 12 or the critical number?
The critical number is 0.7698.
0.7698?
Yeah.
Negative 6.71. Can we go 3 decimals? Okay. Just out of practice, right? Just to keep you guys in the habit there. You guys, can you confirm those answers are right, or anybody think maybe one or both are wrong? Any questions?
Mine's wrong.
Yeah.
I think
Did you do the critical point?
No.
That you did the 12 one?
the 1.39 is the right one.
Okay, what do you guys think the 12 one is?
Negative 0.71.
Negative 0.711? So somehow an extra 6 got in there.
I put 3/4 instead of 1/46.
Got it. Okay, that's easy to mix up because we had 3/4 going on down there.
Yeah,
Okay, so we agree on that. Okay. So now we look over these numbers, and this is going to work out pretty well. I think what we'd want to do is ignore the fact that the last number is negative, because we're just looking at a distance, and whether one is below or above or that relationship is switched really doesn't matter, right? We're looking at distance. But this one right here, that's the biggest distance, isn't it? The 0.7698. This could have been confusing. I'm glad that Jake picked the numbers that or the ordering that he picked on the subtraction, because if he had said, hey, let's do 1/4 x minus x to the 1/3, wouldn't all the signs in our table be switched, at least on the distances? And so that it might have been tempting to be like, hey, negative 0.7698 is not bigger than positive 0.711, but the truth is we're looking at a distance, aren't we? So whether the distance is negative or positive really makes no difference. We pick the bigger number, and the bigger number is the 0.7698. So we'd want to call it out and say the max distance is 0.7698, and we're done. Your justification is your table and your work. It did say show the work leading to your answer, and I would say that we did. You guys have any questions? Okay, well, let's finish this off real quick with just a little conceptual question. Just this little discussion here. So it says, decide whether each labeled point is an absolute max-min, a relative max-min, or neither. We haven't really talked too much about relative max or mins. That's a little foreshadowing of what's coming up a little bit later on. But let's go through, let's just shout these out one by one and discuss as needed. So what would you say about A?
Absolutely.
That's an absolute min, right? That's the lowest point on that interval. So definitely A is the absolute min. What would you say about B?
Relative max.
Isn't that a relatively high point? I mean, it's not the highest point, but it is a high point, right? So relative max, agreed. How about C?
Critical number.
That's a graph of F, I think we're left to assume, because it just says X and Y. That's just where F is 0. So I would say that that's probably a neither, none of the above. How about D? Relatively low, right? So a relative min, it is a low point, but it's not the lowest point. What about E? Relative max. I mean, it does look like it's a pretty sharp turn there, but Still a max, right? Still a max. What about F? Relative min. It is another sharp turn, but it's still a relative min, right? Still a low point. And then finally, how about G? It's open, right? So you might be tempted to say G is the absolute max, right? But it's not the absolute max because that function apparently doesn't exist right there. And so this one does have an absolute min, but it does not have an absolute max. Take it all the way back to that extreme value theorem. The only way you can guarantee a max and a min on an interval is if it's continuous on the whole interval. This one's not, so we don't have an absolute max. I just want to make note of one other thing here. You can see at the bottom, it's on your notes here too, it says key takeaways from 3.1. You'll find through much of chapter 3 that I have like these little key takeaway things here, just like a really brief summary about here's what I want you to leave this section with. And as you look that over, it says when finding absolute extrema, the candidates are endpoints and critical numbers being where f prime equals 0 or DNE. When you're testing those candidates, you evaluate f of x at each candidate. Isn't that what we've been doing? So this is just kind of the key brief takeaway from the main points of this particular section. You'll find at the end of the chapter there's like another kind of summary or a couple of summaries on how to do some things we haven't quite learned how to do yet, but you'll see that later on. Hopefully these are just like good quick reminders of how to do what you're supposed to do and hopefully remember it. All right, moving on from 3.1. We good? Yeah, Matt.
So you said that for that last conceptual question,
Mm-hmm.
it's that particular kind of function isn't continuous, you can't.
Can't guarantee a max or min.
Okay. If like B was higher than G, could you guarantee that's a max?
You couldn't guarantee it. It would have a max, right?
Okay.
It would. So the EVT, extreme value theorem, it's an existence theorem, kind of like the IVT, right? So the IVT says if you have a function that's continuous, right, then you can guarantee that if you start here and you end here, you hit all the points in between. So if you take away the continuity idea from the IVT, you can't guarantee that it hits all the points in between, but it still could, couldn't it? So this EVT is kind of the same thing. It says if a function is continuous on an interval, then you can guarantee a max and a min. If the function is not continuous on the interval, you can't guarantee a max or a min. It doesn't mean that it doesn't have them, just that you can't guarantee it.
Okay.
Speaking to the existence, like knowing that they exist or not. Make sense?
Right. So if you do know that they exist, can you say?
Oh yeah, you could say that's the max, that's the min. But the EVT just says you can like predetermine whether you can guarantee that or not. Make sense?
So if B was higher than G, then it would be an absolute.
It'd be the absolute max.
Okay.
It would. It would be a relative max and the absolute max.
That's what you're.
It would be both. It would be both.
G cannot be relative because we don't have another point in there.
Yeah, they're not relative because we don't see a pattern of sign change in the derivative. We'll get to that in 3.3. They're just endpoints. All right, so let's take a look at what the whole speed trap was about. It was about this right here, the mean value theorem. So I want you to note a couple of things here in regard to the mean value theorem. And hopefully you'll be able to see the parallels with the speed trap project. Here we go. It says if f is continuous on the closed interval from a to b and differentiable on the open interval from a to b. So this is the idea of the teleporting car. So if you do have a teleporting car, something like a non-continuous or a non-differentiable path, then the mean value theorem is out, right? You can't use it. Yeah, we'll see if we can find one, and then we'll pool our money and buy one, yeah. So if f is continuous, which we assumed that the path driven by the drivers yesterday was continuous, and differentiable, which I think we can all safely assume that that's true too, then we know for sure that somewhere on the open interval there is some number c, and notice what this says. Somewhere f prime of c, somewhere the instantaneous rate of change, right? F prime of c equals the, what's that thing right there? Ouch. Oh. It's not the derivative. Okay, difference quotient, yes. Keep going with that. No, the thing on this is not the slope of the tangent line. Come on. You're seeing this out of context and you're seeing things that aren't there. Not distance formula. It's some kind of average. Yes, keep going with that. It's average rate of change, yes. I mean, that's what it is. Do you guys recognize this? I know you do. Isn't that what the right side is? It's the average slope, or average rate of change. So this over here, f prime, that's the instantaneous rate of change. And over here, this is the average rate of change. This is the reasoning that the police used. The police said, hey, if I know this thing on the right, if I know your average rate of change, because I know your distance and your time, then I know for sure that your instantaneous rate had to have been reached at least one time. Isn't that what the police did? They said, I know your average rate, so I know that your instantaneous rate had to be that average rate at least once. Isn't that exactly what the police did? They calculated your average rate using D equals RT, really basic stuff, but then they said, you know what, we can take that and say your instantaneous rate had to have been that, and the assumption is that your path was continuous and differentiable. See it? I hope you do. Okay, so I don't know, this is just a repeat. I don't know why this is in there. This is just written the same. Here's a different way to think about it. If f is continuous and differentiable, then somewhere the blank slope equals the blank slope. What do you think goes in the blanks? Instantaneous slope, yep, equals the average slope. Let me draw a little picture for you. I think I've got room. I think you've got room too. So if I've got some graph, and we're going to call this graph f of x, and this graph does something like this. Hang on, I want to do a little bit different. I'm going to go with that right there. So there's my graph of f of x. It's on a closed interval from a to b. I've put some endpoints there. You can just kind of see, all right, fine, that's f of x. Maybe it's a parabola, a cubic. I mean, who knows what it could be? It could be a sine graph. But that's my graph of f. If I was going to graphically represent the average rate of change, wouldn't it be fair to say that the average rate of change or the average slope would look something like that? I tried to make it a straight line. That make sense? Okay, now the graph that I drew for f of x, isn't it continuous and differentiable? There's no sharp points, and there's no jumps, gaps, or vertical asymptotes. So that means the mean value theorem applies. What that means then is that I should be able to locate a point on the green graph whose slope matches the average slope. Do you see it? I'm thinking it's like right about there. Slope of the tangent line. Do you see how it's parallel to my average slope? Is that fair? So I would say for me, there's one time where I actually hit the average rate of change. If we wanted to look at a little more complicated graph, how about this? What if I said, here is f of x, starts here, goes up, down, up, like that. Then I would say my average slope would be illustrated by something like that. How many points do you see now where that average slope is reached by the green graph? I'd say, yeah, probably two. I'd say maybe one right about there and another one right in there. You see it? So the mean value theorem only applies if the graph you're dealing with is continuous and differentiable on the interval. And if it is, then you know that if you calculate the average rate, you'll actually find that average rate somewhere on the curvy graph. That's what the police did. Does that make sense? Hope that you will be able to make that good connection. Okay, so one of the things that's emphasized here, this is not a cookie cutter thing. One of the things we're going to for sure emphasize, AP folks will emphasize it too, and that is the conditions for a theorem. The conditions are continuity and differentiability. So before you just like randomly apply the mean value theorem to some situation, check, is the function continuous and differentiable on the interval that we care about? You're going to find some times where maybe it is and maybe it isn't. So make sure you check and make sure you know those conditions for the MVT. So let's do an example or two here. Let's try example number 1. So example number 1 says, determine whether the mean value theorem can be applied to f on the closed interval a, b. Let's determine that first. So what are the conditions for the mean value theorem? Okay, so that's right. Here's the function right here. How would you describe that function? Cubic, yeah, it's a cubic or a polynomial. And polynomials we know from before are always continuous, and always differentiable. So we want to actually make a note of that. We want to say something like f of x is continuous and differentiable on the interval from -1 to 1. Therefore, the MVT can be applied. You want to make sure you make note of that. It's an important condition, because without that, we really can't use the MVT. So write that down, and now we can use the MVT. So if the MVT can be applied, we want to find all the values of C in the open interval. If the MVT cannot be applied, explain why not. Well, we don't have to do that part because we already know that it does apply. But now we want to find all the values of C on the open interval a to b such that, does this look familiar? In your own words, can you describe what that's saying? Oh, but it's an equation, so I agree. The part of that says average slope. What is?
Instantaneous rate of change equals the average rate of change.
Yeah, we want to find, you said it really well. We want to find out where the instantaneous rate of change equals the average rate of change. So let's find those things here. Let's find f prime first. Lainey, what do you have for f prime? Or what might you have for f prime?
3x squared plus 2.
So 3x squared plus 2, agreed. And then f of b minus, what are my b and my a? I don't see those anywhere. Do you see those, Ben?
Plug it in from -1 and 1.
Yeah, -1 and 1 are the b and the a, right? So b is the higher number, a is the lower number. So this would supposed to equal f of 1 minus f of -1 all over 1 minus -1. I'm going to replace the x with a c here in a second because it wants to know where f prime of c equals this. If you left it as an x, it's probably not the end of the world, so don't stress about that too much. But we do need to evaluate the right side. What is f of 1 minus f of -1? Let's start off with this. What's f of 1? 5? I don't think so. How about 3? And what about f of -1? It's -3. 1 plus 1, of course, is 2. So I'm getting 3c squared plus 2 equals 6 over 2. Also known as 3. And we're just solving this now, right? So we do the regular old equation solving type steps. End up with c squared equals 1/3. So what does c equal? Yeah, don't forget the plus or minus. Plus or minus the square root of 1/3. Please don't worry about rationalizing anything. We just leave it like that. The last thing you want to check is make sure that any answers you get actually fit within the interval that you were given. So plus or minus root 1/3, does that fit within -1 to 1? It does, yeah. So we'd leave both of them. Apparently there are 2 spots. It's a cubic. Like we saw earlier, it's possible for a cubic to have 2 places where you actually hit that average rate of change. Johnny, go ahead.
So in the equation of f prime c equals fb minus fa, why are you plugging b and a into derivative function? Why don't you plug it into the original function?
Okay. I was plugging into the original function. So hold on. So I guess I want to make sure I understand. So f of 1 means plug 1 into f.
Yeah, so that'd be 5, wouldn't it? Because x, oh wait, that's 3. Yeah,
I think you're mixing the two up. Yeah.
my bad.
No, it's all good. Definitely want to ask. Not a problem at all, Johnny. Thanks for asking. Anybody else with a question? So, oh yeah, go ahead, Riley.
So if the MVT could not be applied, how would you want us to explain that?
So yeah, so what you would say, like you'd have to have some proof for it, right? So maybe the function was not a cubic, maybe it was something more complicated, and you did some kind of analysis and you're like, oh my gosh, look, it's not continuous on the interval. What you would say is MVT can't be applied because f of x is not continuous at 0. I'm done. And you'd have to have work to back that up. You can't just like make something up, right? You have to have some analysis to back up what you're saying. Yeah, it's very possible that you could have, hey, you know, f of x is not differentiable somewhere on the interval, so therefore the MVT can't be applied, and you just move on. Anybody else? All right, cool. Well, let's take a look at one of our other limit from the left. So limit as x approaches pi from the left. And that would be that line, right? X over pi plus 3. And that hopefully equals the limit from the right. And that would be the sine. Such a beautiful question. This makes you think a lot. And that's supposed to equal g of pi. But wouldn't g of pi be the same thing as the sine graph? So I'm just going to write it as g of pi. Okay, so let's evaluate. If I'm going to evaluate a limit, isn't potentially the easiest way just to plug it in and see what happens? Direct substitution. So if I try direct substitution on the first limit, what do I get? Pi over pi plus 3. 4. Okay, so 4 equals possibly, if I plug in a pi into if I try to evaluate it in the second one, sine of pi over 2 is times 4. Look at that.
Wow.
And so that means 4 equals 4 equals 4. So that means it is continuous, and so we can use the mean value theorem, right?
No.
Not necessarily. We need to check differentiability as well. Okay? It is continuous, so that's good news, but we need to check differentiability as well. So to do differentiability, I need to find g prime first. So g prime, what is the derivative of 4 times sine of x over 2? Got to differentiate both parts. Think of x over 2 as 1/2 x. Suggestions on what the derivative would be? We think
Is it 2 cosine x over 2?
it's 2 times cosine of x over 2. Don't forget the chain rule factor. The derivative of x over 2 would just be 1/2.
Yeah.
Times 4 gives him that 2 instead of the 4. That makes sense? It's a chain rule. Might be handy to know tomorrow. Just saying. And then how about the other one? How about the line? What's the derivative of x over pi plus 3? What is it? It's just 1 over pi. Good. Okay, so g prime is those two pieces right there. This is if x is bigger than pi. This is if x is less than pi. We don't know what's happening at pi necessarily.
Well, but x is greater or equal to pi is the top.
Yeah, but so we don't know if f prime, or I should say g prime, we don't know if g prime really does exist at pi. So this would be like a really technicality little piece here. I got to just leave it open at this point because I don't know. I don't know if it really is differentiable. If you did that on a quiz or test, I'm probably not going to get too upset. Don't worry about it. All right, so if we try this out, don't we need the left-hand derivative equal the right-hand derivative? What happens? So if we did something like limit as we approach pi from the left of g prime is supposed to equal the limit as we approach pi from the right of g prime. When we actually evaluate those limits from the left, what do we get? Don't we get 1 over pi? Does that make sense? What about from the right? What do we get? Say it again. Cosine of pi over 2 is 0. 0 times 2 is 0. Oh my gosh, look at that. They're not equal. What does that mean? Not differentiable. Therefore, can't use the MVT. So we would say, based on the evidence, we would say something like G is not differentiable at x equals pi. Therefore, MVT does not apply. So Riley, this would be that case, right? This would be a situation where you checking the conditions makes all the difference, because you could race off and just find f prime of c equals f b minus f a over b minus a, and you may or may not get an answer for it. But if you would have just said, hey, look, it's not differentiable, you stop right there. Definitely a lot involved in that. I'm not saying that it's easy, but it's the right thing to do because it allows you just to stop when it's time to stop. Nick, go ahead.
So differentiability matters for MVT, but does not matter for intermediate value here.
That is correct. That is correct. Any other questions? All right, well, let's see if we can get a little ways into our final question of the section here, which is this one right here about hot water dripping through a coffee maker. Take a second and read it. One of the reasons I included this is it includes data that's not given in an equation like the other ones we've done. It's data given in a table. And so this is a little bit different. Sometimes it takes a little bit of time to get used to this. We've done others like this, but figured it'd be good to put one of these in here. It says hot water is dripping through a coffee maker, filling a cup of coffee. The amount of coffee in the cup at time t from 0 to 6 is given by a differentiable function c, where t is measured in minutes. Values of c are given in the table below. This is actually an old AP question, free response, in which I've just taken one part of it. So the question below says, is there a time on the interval from 2 to 4 at which c prime of t equals 2? Justify your answer. So remind me again, what is the table telling me about? Yeah, specifically c, which is the amount of coffee. So c prime, what would c prime, which is what it starts talking about down below, what is c prime about? The rate of change of the, is it amount of coffee or temperature of coffee? It's amount. So c prime would be the rate of change of the amount. Okay, so let's think this through. Notice what the question is asking. Is it asking what time c prime equals 2? What is it asking us for?
Does it happen?
Yeah, so aren't they essentially asking, does this answer potentially exist or not? Right? It's not asking what the answer is. It's just saying, does the answer exist? And if it did exist, maybe we could find it. But it's not interested in that. It just wants to know, does it exist? So how does c prime relate to the table? Say again?
Derivative of the function.
Okay, and derivative is on a graph is also known as rate of change, also known as slope of the tangent line, right? So c prime is related to the table, and that c prime is the average rate of change, the slope of the tangent line. So it wants to know, is there any place where c prime t equals 2? Let's be police on this. Think this through. If I could find an interval where the average rate of change is 2, could I guarantee then that c prime equaled 2 somewhere? Does that seem reasonable? So if I could find some interval where the average rate of change is 2, then I know for sure that c prime would have to be 2. But all that is predicated on what conditions? And how does this question take care of that? Doesn't it just come right out and say it? It says, given by a differentiable function c. So they're telling you c is differentiable, and differentiability implies? So here's how you'd start this, and this is, we'll end this here. We'll pick this up again at a later time. So here's what you'd do is you'd say c of t is differentiable, therefore also continuous on the interval from 0 to 6. Therefore, the MVT can be applied. So you'd want to mention, hey, it's differentiable, like they said, but that also means it's continuous. Therefore, we can use the MVT. So what would go on from here is like investigating each of the little intervals and see if we can find a spot or an interval where the average rate of change is 2. Therefore, we'd be assured that c prime would equal 2.
Need to be on the interval that they want between 2 and 4, wouldn't it?
From 2 to 4, yeah. But there's 2 to 3, 3 to 4, and 2 to 4. So there's 3 of them, right?
Yeah.
So we just need to investigate that. And if you do the quick math in your head, you can see that 2 to 4 works pretty well. So, hey, I hope you guys have a wonderful day. See you tomorrow afternoon for your test.